Okay, so welcome everyone. I think we're going to go ahead and get started because we are tight on time. And I would like to begin. I put this slide up here just for some guidance on what we're doing, approximate timing. And my colleague Faith Karanja is perhaps delayed, but she is going to provide a general welcome to everyone. Thank you to all of you who have responded to our invitation and registered for this webinar. I'm Professor Megan Cope. I'm at the University of Vermont in the US, and I would like to kick us off with first just a very brief overview of what this organization and this group is. The International Geographical Union is, as it suggests, an international organization promoting and supporting geographers around the world, from undergraduate students all the way through retired professors. And the way that the IGU works is to divide into research or interest areas. And so this commission, which are called commissions, right? And so this commission, which was only started, excuse me, only started about 7 years ago, is focused on research methods. And we really cover the whole span of different kinds of research methods, all the way from, very advanced, as we see today, some AI and modeling and quantitative work, all the way to art-based research and everything in between. So we're led by a steering committee of 9 faculty from all over the world, and our goal is to really bring us together, support and connect people. And along those lines, we have a website, so I'll point you to that address there in the bottom right. And we also have some social media on Blue Sky and on LinkedIn, so please give us a follow. We will try to announce things through there. You can also become a member of our commission. It's free, it's open to anyone, and you can do that on the website, through the website. After the webinar is completed, I will send everyone who registered a feedback survey. We'd love to hear some feedback from you, partly about this webinar, but also suggestions for future webinars and topics that you would like to know more about. And let's see. So we are going to, I will introduce our guest in a moment. We have some support today from 2 steering committee members, Chiara Giubilaro and Sarah Mills, and they will help moderate questions, but we're going to ask everyone to hold the questions to the end. I will turn the chat function on at the end of the presentation, and you can post a question there or raise your virtual hand. Please use the reactions buttons for that. And just a note that we are recording and transcribing the video, and we'll be sharing it on our website and YouTube. So please moderate your own privacy levels as you feel comfortable. Okay. So I have a very brief introduction for our presenter today, and would like to welcome Professor Bing Zhou of the University of Kentucky. Sorry, I always do that. The University of Tennessee at Knoxville.
They're close. Just two
Yeah,
hours
right.
drive.
I know. I know, but yeah, it's the UTK that messes me up. Um, University of Tennessee in the US, and Professor Joe got his PhD at Texas A&M University in geography, and just kind of some more fun facts is that he enjoys sports, and he's also a professional photographer. So I will stop sharing and ask you to go ahead and take over.
Yeah. All right. Let me try to share my screen first.
Yeah.
Okay, perfect. All right. Can you see my slides?
Yes. Thank you.
Okay, great. So, I'm really honored to be here to be the presenter of this IGU webinar series, and thanks, Dr. Kobe, for the invitation. So I'll get started. So the topic for today's webinar is artificial intelligence in geographic research. Before I go any further, please allow me a few more seconds to self-advertise. So now I am an assistant professor at Department of Geography and Sustainability at the University of Tennessee in Knoxville. And I'm also the director of the Geospatial Responsible AI for Nature Human Dynamics Lab, also known as the GRIND Lab. And the vision of my lab is to foster a resilient, equitable, and healthy society through responsible and geospatial thinking. And currently, there's two major research focus. The first one is GeoAI in disaster resilience and human well-being, and the other part is geospatial informed GeoAI and responsible GeoAI. So let's move on to today's topic. So today I will cover three major parts. In the first part, I will introduce what is AI in plain language. Then I will briefly mention the chemical reactions between AI and geography. And in the third part, I will introduce briefly some of my work that are highly relevant to the application of AI. So, what is AI? Also known as artificial intelligence. So, a working definition would be AI is the engineering of systems that perform tasks we would call intelligent when a person does them. So, in simple words, it is machines trying to mimic humans and do intelligent things. And the concept of AI actually emerged a long time ago, which is around the 1950s, and what we call the symbolic AI emerged. And this figure right here shows the history of AI, which is marked by five key milestones. In 1980s, statistical learning appeared, and this is also known as machine learning nowadays. And then in 2012, the deep learning took off. And in 2017, with the introduction of the attention mechanism, a new model design called the transformers pushed the performance of deep learning to the next level. And in around 2022, foundation models, which are usually large scale pre trained models such as ChatGPT, Gemini, started to emerge. And now we'll dive a little bit deeper into machine learning and deep learning, which are two popular terms we often hear. And the figure right here illustrate the relationship among AI, deep learning, and machine learning in a hierarchical manner. So part of AI is machine learning, and part of machine learning is deep learning. The scope just narrows. And let me explain what is machine learning and deep learning. So machine learning is essentially an optimization problem in which we need to determine the parameters of a function. Usually, we have a lot of input and output data pairs and assume that we can, in some way, predict the output data using the input data. For example, house price data, and the input is the median income of a location, and the output is the house price of that location. And the data pairs we have is usually called the training data. And the process of machine learning is try to nudge the parameters in the function of the input variable x such that the output y is closest to the truth of the training examples. So terms like linear regression, logistic regression, support vector machine, decision trees, and random forests are all belongs to the machine learning category. And for the training data we usually separate them into three sets, namely training sets, validation sets, and the test set. The training set is usually used to determine the parameters of the function, and the validation set is used to determine the hyperparameters during the training, and the test set is used to evaluate the performance of the trained function, or we call it model. And another popular term is the neural network. We call it neural network because we're building a model that looks like the figure shown here, with nodes and connections, which resembles how neurons in our body pass signal. Although some neural networks might seem quite intimidating, the underlying theory can be quite simple. I think we're quite familiar with linear regression and logistic regression, and that they can be considered as a neural network with only the output layer. And the nodes are the coefficient in the linear regression, and the edges between the nodes are the calculation of coefficient and the independent variables. And considering the linear relationship is a little bit limited, and it might fail to capture the complex nature of phenomena, therefore, people try to stack more linear layers together and calculate them one by one in a sequential manner. And between each layer, we add something called a activation function to make the calculation nonlinear. And in this way, the entire calculation becomes a nonlinear model. And the more layers we added to the model, the deeper the model becomes. And the deeper here becomes the deep in the deep learning. So for deep learning, the concept of training is quite similar. It's almost identical to machine learning, except we're talking about large scale nonlinear models. And deep learning model I mentioned a moment ago is what we call the artificial neural network, or also ANN. And of course, there are many other variants of neural networks, and each one of them will have a special focus. For example, the convolutional neural network is very good at image-related tasks, such as image classification, image segmentation, etc. And it basically applies something called a kernel and uses sliding window approach to identify the features in the image so that the image-related task can be performed quite well. And when we're talking about deep learning, I cannot fail to mention the transformers, which is a groundbreaking model developed recently. Not recently, it's almost like 5 years ago. And so initially, the transformer is designed to process natural language. And transformer is constructed based on the attention mechanism, which is basically let the model learn the meaning of a word based on how much the meaning is impacted by other words in a sentence. And now transformers have been adapted to many other domains. And the transformer is the core of most of the pre-trained foundation model nowadays, such as ChatGPT, Qwen, and Gemini. So while I have presented a very brief explanation of AI, and I hope you will have a sense of what AI is, and now I will briefly show how AI can be used in geography. And here are some examples. So for deep learning models, they're really good at image processing, and they can be great candidates for processing and analyzing remote sensing images, of course, such as deep learning can be used for semantic segmentation of remote sensing images, used to detect changes, to do super resolution, and also to do object detection. And another thing that deep learning models usually good at is making predictions. And also, they can make predictions based on images, and it's quite it is used a lot in urban analytics, and also a variety of other predictive tasks, such as weather forecasting, downscaling, wildfire flood risk prediction, and biodiversity or species prediction. And another branch of deep learning is the graph neural network, and they can be used to model network systems and are really useful for network system analysis, for example, mobility and trajectory prediction. As I mentioned, model size nowadays are unhinged, and we have a lot of general purpose foundation models emerged recently. And in geography, we're also trying to build our own geo foundation models. For example, a typical example is the Alpha Earth model published by Google last year, which is essentially we're trying to turn the Earth's observation data of a location to a series of numbers, which we call embeddings. And the embeddings can be used for various downstream tasks without training or with only limited fine-tuning. And these tasks includes land cover prediction, change detection, and also varieties of other tasks. So basically, the embedding model is trying to represent the place and assuming that the embedding can understand the place. And that's the geo foundation model nowadays. All right, so now I'll move on to introducing some of my work on geo AI in disaster management. Let us take a look at this hazard map here. Well, I have to say that we are quite unfortunate to live in an age that is so hard to even survive, because we were surrounded with numerous type of hazardous events, such as geophysical events, meteorological events, hydrological events, and even health issues. And uh, this figure is made by NOAA, demonstrating the billion-dollar level disaster in 2024. There have been 24 confirmed billion-dollar level weather and climate disaster events in the United States. And this events result in over 418 fatalities. And for some reason, NOAA stopped making these maps, but it does not confiscate the importance of disaster research. And also, I think we're lucky enough to be in an age of hope. The marriage of AI and geospatial data science provides tools that empowers integration of emergent multi-model big data and enabling smart environment sensing, disaster management, intelligent resource allocation, and so on and so forth. So first, let's take a closer look at one devastating event, Hurricane Harvey. So Hurricane Harvey was a powerful Category 4 hurricane that made landfall on Texas Gulf Coast in August 2017. The storm caused an estimated $125 billion in damage as the costless tropical cyclone in the U.S. history at the time, and also resulted in at least 107 direct and indirect fatalities. And beside the wind damage, it is particularly noted for its unprecedented and catastrophic rainfall, which led to historical flooding. And the news report on the left actually shows the emerging condition it caused in Tennessee. And in addition to the heavy flooding in the real world, in the virtual world, Hurricane Harvey made the social media platform flooded with rescue requests as well. Harvey was one of the first events in which social media played crucial roles in fast response and rescue missions. For example, in Houston at the time, around 10,000 Houston residents were trapped in their homes or on their way to evacuate, and the local police department rescued only about 30% of them, because at the time, the 9/11 system was overloaded, and many Harvey victims turned to social media for assistance. Users post help requests or rescue requests on the social media platforms, while volunteers and responding agencies search for those messages and send help. And here are several sample rescue requests from Twitter. At that time, harvesting this information was most done manually, which is extremely labor intensive and inefficient. And in that situation, inefficiency could be a matter of life and death. So we're thinking, is it possible to design and tune a deep learning model to automate and expedite the process? And actually, we believe so. And but before going into the deep learning model design, we need to figure out how human beings make decisions. How do we know if a social media post is a rescue request or not? Well, then we just need to decide if it is a rescue request. It's quite simple. But if we break down the process, it's actually a two-step approach. So first, we need to understand the language, and then we need to make decisions on based on the understanding whether the message is a help request or not. And lucky enough, computers tackle this problem similarly. So for the first part, understanding the language, we do have a counterpart in the natural language processing domain called the language models. And it can be as simple as a dictionary or as complicated as a huge neural network. And for the second part, categorization or making decisions, this is where deep learning or deep neural networks comes handy. Therefore, the question has been decomposed to design and train a feasible language model and classifier combination that can actually identify rescue requests. And when we took a look at the recent history of natural language processing, the technology is developing really fast. And the figure right here condensed 15 years worth of work into 8 milestones. And every single one of them lays solid foundation for the later. And in 2018, the introduction of a variety of transformer models, which benefit from the attention mechanism, as I mentioned a moment ago, and they pushed the performance of language model to the next level. And one of them, the bidirectional encoder representation from transformers by Google, also known as BERT, has outperformed previous models and achieved state-of-the-art performance. And we choose BERT as our language model in our study. And here is a architectural design of the model we're using. So basically, we're stack a multi-layer perceptron or other deep learning neural networks on top of BERT to make predictions. And we have explored several model architectures, for example, stacking a simple multi-layer neural network, stacking a long short-term memory neural network, and also a convolutional neural network, which is stacked on the hidden states of the BERT model. And after some initial experiment, we noticed that the convolutional network model performs the best. And here is a table shows you the performance of the model compared to a series of other relevant models. So basically, we're trying to use the model to identify help requests of social media data. And as we can see that our model, which is marked with the red star there, outperformed all the other baseline models. And it outperformed them by approximately 10%. And using this model, we were able to accurately and also agilely harvest rescue requests from social media data. And this work is one of the very early studies that bridges large language models, GI science, and disaster management. And it also inspired numerous follow-up studies. And this work is supported by the NSF, and also I provided citation here. If you're interested in this one, you can take a look at the published work in Computers, Environment, and Urban Systems. And let's get back to the case of providing rescue during Hurricane Harvey. So the study I talked about just now can accurately identify help requests, but we still need to figure out the location of the help request in order to send help. And let alone the geotag tweets made up only around 1% of all tweets. If we take a look at the rescue request sample here, we notice that the people requesting for help prompt to mention the address in the textual content rather than using geotags. So if we can automatically extract this address information from the textual content and locate them on the map, and this will drastically reduce the workload of the first responders. However, the first existing tools that can handle this type of task is limited. Therefore, we decided to give a deeper dive with the knowledge we have in natural language processing. So to formalize the task we talk about, we're actually dealing with a general geographic task called the geoparsing, which can be represented by the web application shown on the left. And geoparsing contains two steps: toponym recognition, which is extracting address from text, and toponym resolution, which converts address to coordinates. And toponym resolution is also called the geocoding, which is usually done by using available geocoding services such as Google Geocoding and geocoding service provided by the Texas A&M University. And we are only focusing on the first part. So toponym recognition is essentially a subtask of name entity recognition that involves identifying and classifying name entities in text into predefined categories, such as person, organization, location, time, and so on and so forth. And in deep learning, it is a token level classification task where the input is a chunk of text and every single word in the chunk is a token, and the output is a specific label assigned to each token. And this is the part we're trying to optimize by designing a novel deep learning model. I think we're all quite familiar with the Tobler's first law of geography, and this is quite obvious. And I don't know why this everything is related to everything else, but near things are more related than the distant things can be considered as a law. But it is fun. But it is the fundamental spatial dependence and the spatial autocorrelation that inspired my model design in this case. So we're considering that the location, the words in a location name, are close to each other and comes in groups in a sentence or documents. So we're considering taking advantage of this clustering feature and see if it could help to enhance the performance of the toponym recognition. And similar ideas has been applied by scholars to detect patterns from remote sensing images to enhance the performance of crater detection. And in this case, we're trying to use this theory in toponym recognition. And this is the model design of the toponym recognition model we developed, which is called the TopoBERT, a plug-and-play toponym recognition module harnessing fine-tuned BERT. So for this model, we're still building upon the language model BERT, and we're extracting the hidden layer out of BERT and to create a one-dimension embedding concatenated by the convolutional after the convolution. And so the way we do convolution is to use a one-dimensional convolution because we think that using a one-dimensional convolution, we're able to identify those clustering effects of the location names. And followed by the concatenated layer, we attach a multi-layer perceptron to it to perform the token level prediction. So this is the model design of the toponym recognition model. And we have tested our model on a series of benchmark data sets and compared to a series of baseline models. And the performance is shown in this table right here. And we can see our model is marked with the dark blue color at the bottom. And those cells marked with magenta indicates the best performance. And we can see that our model outperformed other baseline models in the majority of benchmark data sets. And this work was published in the International Journal of Digital Earth, and the figure on the right demonstrates the location of tweets processed by TopoBERT during Hurricane Irma. And this work can alleviate a challenge in geolocated social media data harvesting, and at the same time, it also provides solution to a general geographic problem. And it can also be easily integrated in numerous tasks that requires extracting location information from texts. All right, so previously, based on the two deep learning model we developed, we're able to identify help requests and we're also to locate them on the map. So the next step is that we're trying to delve deeper by harvesting those help requests from social media and trying to examine the patterns of the social media post during 3 different hurricanes, namely Hurricane Harvey, Hurricane Irma, and Hurricane Ian. The reason why we choose this hurricane is that Hurricane Harvey and Irma both took place in 2017 at almost the same time, and the Hurricane Irma and Ian both made landfall on Florida. So it would be interesting to see if there's any specific patterns due to these attributes. So, based on the data we harvested, we identified four type of help-related posts in social media platforms, namely humanitarian help request, lost animal-related help request, and also people reporting infrastructure malfunction in social media platforms. And there are also people offering help or providing shelter information in social media platforms. And for this research, we're trying to answer three research questions. So the first one is, can tweets be categorized into fine-grained topics with deep learning models? And the second research question is, what are the spatial and temporal patterns of the tweets during the three selected hurricanes? And the third research question is that, can indices derived from tweets under fine-grained topics be an auxiliary data source to better assess disaster damage at county level? So for this one, we're still trying to use a deep learning model to harvest the social media posts in fine-grained topics. So we made minor changes to the victim finder model we mentioned in our first case study. And in that study, we're basically trying to identify help request, which is a binary classification task. And for this one, we're identifying four different classes. So we need to turn the model into a multi-class classification task. And we then train the model and evaluate the model on the testing data set. And this is the result we get from the model performance, which is quite good. So I think the model will be reliable enough to be used to harvest the entire data set. And after the data harvesting, we do some spatial analysis and also temporal analysis. And let us take a look at the temporal patterns of the fine-grained social media data first. So here is the figure showing the temporal patterns. The y-axis is the number of the social media posts for each category, and the x-axis is the time. And the dashed line in the four different colors represent the four fine-grained topic we talk about, and the vertical line indicates the time of the hurricane landfall. And based on the figure shown here, we observe that the numbers surge around 2 days after the landfall, and there are way more infrastructure related tweets during the Hurricane Irma and Ian than Harvey. And one interesting pattern is that for Hurricane Irma and Ian, the number of disaster-related tweets decrease and dwindle with the number of power outage. But for Hurricane Harvey, the number of power outage remained high for a period of time after the number of tweets diminished. And this can be explained by the fact that Harvey caused a lot of flooding and the power outage during Hurricane Harvey because that was caused by inundation, and the power plants and substations are deeply influenced by that. And this takes longer to recover. And then let us take a look at the spatial patterns. And this figure shows the spatial distribution of the disaster-related tweets during Hurricane Harvey under fine-grained topics. And this figure just provides you an intuitive sense of where those tweets are. And to further evaluate impact, we need to normalize the number of tweets by population at county level. So we develop a Twitter's index called the DSI, which is the normalized Twitter accounts. And this is this figure right here shows the spatial distribution of DSI. And let us take a look at two case right here, which is the humanitarian help request and the infrastructure malfunction. So this is a zoom in view for these two scenarios or these two type of Twitter data. The red line in the figure indicates the hurricane track. And simply by eyeballing them, we observe that across three hurricanes, the infrastructure malfunction related posts cluster around the hurricane track, but the help requests exhibit different patterns. So for Hurricane Harvey, the counties that exhibit the most intense help requests are not so close to the track, but in severe flooded areas, according to reports. This might indicate that the rescue requests for Hurricane Harvey are largely due to flooding. And for Hurricane Irma, The Monroe and Polk County lies on the track of the hurricane, but the St. Louis County is a little further from the track. And those are the most impacted area, according to the infrastructure malfunction tweets. And referring to the rainfall animation of Irma, we can see that St. Louis County experienced heavy rainfall that caused flooding, which result in a strong signal of help request. And for Ian, the spatial pattern of help requests and infrastructure malfunction posts are quite similar. And this indicates that the severe wind might be the major cause of damage during Ian. And another task for this study is about disaster damage prediction. So to make sure we are on the same page, that this study attempts to investigate what are the most influential factors and how well the assessment can be when we use some socioeconomic factors, some geographic factors, and adding some disaster-related social media indexes we designed to assess disaster damage, which is represented by the number of insurance claims at the county level. And for the analysis, the socioeconomic factor I mentioned include these socioeconomic factors. That includes the population, the youth population, education level to the employment rate. And for the geographic factor, we select these are the 4 geographic factors we select to mimic the impact caused by the hurricane. And they are threat level, which is essentially the kernel density estimation based on the track of the hurricane, as well as the intensity of the wind along the track, and also the distance to the track, the distance to the landfall point, and distance to the coastline. And these 4 are the geographic factors. For the analysis, we first conduct a pilot analysis, which is a correlation analysis between the damage caused by the hurricane and also the social media index we derived, and we can identify a very strong correlation between these two. And then we conduct a multicollinearity test and to exclude some correlated variables. And after the multicollinearity analysis, and here are a list of the independent variables we use for the final regression analysis. So basically, we're trying to use all of these independent variables to predict the number of insurance claims at county level. And here is the result we get. So in the case of Hurricane Harvey, when we use only the socioeconomic factors in the prediction, the adjusted R-square is only 0.06, which is extremely low. And after appending the geographic factors to the regression analysis, the performance enhanced and achieved an adjusted R-square of 0.26. And when we add the social media index, the adjusted R-square reached 0.809, which is significantly higher than the 2 previous experiments. And this indicates that adding the fine-grained social media data can improve disaster estimation. And for Hurricane Irma and Ian, we only observe a boost of performance when adding the geographic factors, and the performance barely changed when adding the social media related indices. And this pattern can be explained by the factor that during Hurricane Harvey, the major cause of damage came from flooding, which can be properly represented by a social media post, while the damage from the Hurricane Irma and Ian are more likely to be directly wind damage from the hurricane. Therefore, the geographic factors become proper representatives that help better estimate disaster damage. And if you would like to know more about this research, please refer to this citation right here. And this work had been published in the Annals of AAG recently. All right, so due to the limited time, I can only share limited details about this research, and I chose to share some of my earlier works that I have been done, which tells a whole story and provides you with a niche in disaster management in which AI is applied. But definitely expect for more. So let me briefly mention some of our recent work. So regarding disaster damage estimation, in addition to relying on semantic information of geospatial big data, we're also attempt to explore a more direct approach, which is the vision-based approach to estimate disaster damage. So the first thing that comes to our mind is just trying to use the Street View images to estimate disaster damage using deep learning models. And the existing Street View related research that focus on disaster damage estimation focus only on the post-disaster Street View images. And in one of our previous publications, we're trying to integrate the pre-disaster Street View images and trying to see if adding the pre-disaster images and combine it with the post-disaster ones can enhance the performance of damage estimation. And also, we explored the use of large language models in automate the data labeling procedure. And in this study, we used two different type of models. The first one is ConNext, the other one is Stream Transformer, and we tested the performance of models on this disaster estimation task based on the pre-disaster image and post-disaster image. We explored different scenarios, and the result shows that by incorporating the pre-disaster image, the damage estimation performance can be significantly enhanced. And this work is published in the Computers, Environments, and Urban Systems. And if you're interested in this work, I can refer to this citation provided right here. And in another recently published work, we're also trying to explore something else. Currently, we're working on place representation. So we're trying to explore, is it possible to use a deep learning model to represent the place so that we can use this representation for a series of downstream tests to enhance the performance. And one of the studies is about cross-modality or multimodality generation in order to understand the place better. And to be more specific, one of the recent published work is that we're trying to use soundscape to generate a Street View using a deep generative model. And this work has been accepted by the top tier computer vision conference, CVPR. And if you're interested in this work, please refer to the citation provided here. And so I have introduced how AI can be applied in geographic research. So how about use AI to do geographic research? And so this is a project we're recently working on. We've been trying to build an autonomous research agent based on the most powerful off-the-shelf large language model, the Opus 4.7, which is developed by Anthropic. And this is what we came up with. We built a research agent called NOAA that can significantly accelerate the geospatial research. And it is built on a tool called Cloud Code, which is a command line tool. And if you install the Cloud Code command line tool and download our NORA platform and install it, it can easily change entire research pipeline by simply a simple prompt. And so basically, we provided a skill called the full pipeline. And you can use this full pipeline skills followed by a brief introduction of the research topic you're interested in. And this, the language model beneath this framework will help you to do the literature review and to explore novel research ideas and also automatically design experiment, deploy experiment, execute experiment, providing experiment report, and also draft a very comprehensive research report based on a simple prompt you provided. And also we include a lot of human checkpoint for you to make decisions as well. So by using this tool, I think the efficiency of geographic research can be greatly enhanced. And if you're interested in this tool we built, I have provided a link to the website right here. And the website also provide a link to the GitHub repo. And the installation is quite simple. It can just refer to the documentation in the GitHub repo, and probably play around with this tool by yourself if you're interested in this one. And here are just two screenshots of the tool while we're doing some demo research. Yeah, I think that's it for today's presentation. I really appreciate the time, and questions are welcomed.
Thank you so much. This was fantastic and a really enlightening introduction for many of us who are not in this field. And I really hope my sincere hope for this wonderful kickoff to our series on AI and research is that regardless of background, that everyone was able to see something that was meaningful for their own research and perhaps could be used. I have turned on the chat, and I'm going to recommend that folks who have a question could type their question into the chat. And of course, we're also happy to have a verbal question. So if anyone would like to raise their team's hand, that would be helpful. I cannot see all participants at the same time, so if I'm not seeing your hand, please feel free to put something in the chat. And I will say also that I will need to give folks permission to let's see, trying to make it so that everybody can speak. So I have a quick question just to kick us off, and wonder if, and there will undoubtedly be more in a moment. I'm curious if, I'm sure that a lot of folks seeing your work would feel like, oh, this is something that is very team-based kind of work. Like maybe you need a number of colleagues and researchers involved. Would you say that that is true, and that there are that this tends to be the kind of work that is larger teams kind of bringing lots of different types of expertise in, or is there are there individuals who are perhaps making groundbreaking insights in this field?
Well, thank you, Megan, for the question. It's a really good question. So I think it really depends on what you want to achieve and also your personal skill set. So I think currently, based on a recent literature review we're doing, for the GeoAI part, the geospatial artificial intelligence part, the majority of the literature is still focusing on applying AI method in solving geospatial tasks. So if that is the case, that for the technical part, it might not be that intimidating because at least for nowadays we have AI assistant to help you with the coding. So the implementation part would not be that hard. The hardest part is still like data access or finding the interesting research question to answer. But of course, there are also some scholars who are working on the technical part. For example, part of my work is trying to include geospatial knowledge in the deep learning model design. And there are also other scholars who are working on representation learning or design specific deep learning models to tackle specific geospatial tasks. And they probably need to find collaboration from scholars who are majoring in computer science, statistics, or math. Uh, And so that's for just doing research and produce publication. But if we're thinking about like grant proposal, so we probably usually have a larger scope, and we also need to ground the methodology development on some real world scenarios. And in that case, we usually like include experts from different domains.
Great. Thank you so much. That's super helpful. There are a couple of questions in the chat, and I'll just read them out so that everyone has access. Hopefully, you're able to see the chat at this point, but just to make sure for the recording. My colleague Sarah Mills asked, could you please share with us any ethical challenges with these methods and approaches, or that you feel are significant for AI and methods more generally?
Um, so thank you, Sarah, for the question. I'm just wondering, could you explain more about ethic parts, because ethic really covers a wide range of topics.
It's a great question. Sarah, I can make you a presenter. Okay.
Hi there. Yeah, thanks, Bing. And just to add a little bit of detail, I guess, perhaps for some of us on the call that are brand new to AI plus methods, there's a sense of nervousness maybe around some of the ethical challenges that it may involve. So it was just if you could perhaps provide either some reassurance or just your own reflections on that and how you've navigated it, either in this project that you've just shared around, or just more generally for us as geographers on the call. Thanks.
Well, that's a very good question. So, for example, let me just use the social media data harvesting example. So basically, we're trying to extract location information from social media data, which will involve geoprivacy issues. Um, I'm sorry, I'm sorry, Megan. I hear a very strong background noise. I'm not so sure is it coming from me or yeah. Okay, okay, that's cool. So all right, so let's get back to the social media example. So we're trying to pull location information from social media, and that definitely will involve some geoprivacy issues in this case. And we're also conducting this on like massive data sets, which like make the issue even worse. But the good thing is that there are also a lot of ways we can eliminate geoprivacy issues by using deep learning models. There are researchers who are working on this part, and for the study I'm working on, since we're only using aggregated data, therefore the issue of geoprivacy is not that acute. So that's one of the ethical issues I have in mind regarding the examples I presented. And also, there's also a lot of other ethical concerns. And I have a manuscript under review at the moment called The Responsible GI Science. And in that work, we talk about a variety of things regarding the use of GeoAI and how to use it responsibly. And one of the there are several elements. Actually, there's a lot of elements, including the reproductivity and replicability of the research, geoprivacy, and also bias issue. I saw one of the questions in the chat box asking about the bias issues, and also how to make AI to benefit human well-being. And we have discussed that in the manuscript in detail. So yeah, that's my idea on the ethical issue.
Thank you so much. I'm sure that we're only at the beginning of that conversation. Yeah, so we have just a little bit more time. We have another question from Professor Singh. Wants to know how we can put human responses to land use changes into machine learning. I wonder if you have any comments on that.
All right. If I understand your question correctly, are you trying to incorporate human responses or human perceptions in land use change or land use prediction? If that is the case, there are several ways to do that. First, if we're using social media data as the source of human response, then we can actually encode those response, basically a natural language, into what we call embeddings, and it would put this embedding in a predictive model in land change detection or land use classification tasks. And if we're considering other human perceptions, for example, like human perception based on visual contents. For example, the use of Street View as a representative of human perceptions. We can also do similar things like trying to embed the Street View images into a vector. And this vector can be used for land use, land cover related studies. And also another thing is the alpha Earth embedding I mentioned, which is basically the representation of a place. And also, most recently, Google published another embedding model, which can embed, instead of the physical information, they also embed some information, some social information, such as the POI and socioeconomic variables, and they put in another embedding. And by using this, I think it can also be used to help with land use related tasks.
Very helpful, thank you. I think we have time just for the last question that's in the chat, which is, how does digital sovereignty affect water data sharing, for example, between India and its neighbors? Any thoughts?
Actually, I'm not an expert in water-related data. But I do mention the data accessibility issue in the manuscript I mentioned about earlier. Um, so I don't know. I think it's similar. If you have data, if you have challenges accessing some part of the data, that would definitely limit your research. I think this similar problem exists in the health domain as well. So if you're doing health-related research, that those valuable data are governed by hospitals and universities that has close relationship with the hospitals, and if you're not in their group, then probably you won't have access to the data. And I think that's pretty much a general issue in the academia, the data accessibility issue, I guess.
Wonderful. I was going to say that was the last question, but I just saw that my co-chair, Faith Karanja, has posted a question, and so I wonder if we could just go a little bit over and ask you, and I'll read her question, with regards to use of social media, like in one of your projects, what validation mechanisms do you have in place to ensure that what you incorporate in the model is authentic? Always a
Thank
tricky
you for
word, that word, and authentic.
Yeah, thank you for the question. So the approach we use is quite straightforward. So for the social media data we're using, we're manually label them. At that time, we hired several undergraduate students to do the labeling. So we have around 8,000 Twitter data labeled, and we are training the model and testing the model on the label data. And the performance I showed you is based on the evaluation of the label data. The F1 score is 0.919, which is quite high. So in that case, we believe that applying the model directly to the whole data set could be quite persuasive.
Wonderful. And I'm sorry, we're going to have to stop there. And I apologize to those with additional questions in the chat. What I would like to do is first of all thank Professor Bing Zhou for this wonderful presentation, and do a little digital clapping here, and I will, as I said, send a feedback survey around, and we'd also like to. It occurred to me that perhaps we would like to share all of the citations that you mentioned in your talk, And so I will work with Bing to create a list of those citations and include that in the email that has the feedback survey link. If that's okay with you, Bing, I'm sure that
Yeah.
sharing your own work and that of your colleagues would not be a problem. So everyone will have access to the list of citations as well. So thank you very much to everyone who came to our kickoff event. We are hoping this is a series of webinars on AI and research. And one of the questions, as I mentioned in the feedback survey, is what specific topics or sub-areas within the field of AI and geographic research you would like to hear presentations in the future. We are hoping to organize another event in November of this year, and so we're soliciting ideas and also interested in hearing recommendations for other presenters who may be suitable for this. Again, we welcome you to join the Commission on Research Methods of the IGU, and I will briefly put the slide with the web address on there again. And once again, many, many thanks to you, Professor Bing Zhou.